So good morning, everyone. So I'm Fabrice from RTE. I've been working at the planning, the grid planning department about 10 years ago. And I will, in this workshop preview, I will try to make a quick introduction to tomorrow workshop, so at 11 tomorrow. Where I will present how PyPowSyBl helped us to assess transfer capacity of new interconnections. So first of all, what is transfer capacity? So the transfer capacity is the maximum exchanges allowed between two countries that will be compatible with security standards. So we will talk about N-1 security criterion. So this criteria say that the power grid must be able to cope with the loss of any line. And the second rule is, of course, that power flows on every line must respect their thermal limit. We cannot transmit infinite power on lines. We have thermal limits. And why calculate transfer capacity? Assessing the benefit of interconnection project is one of the goals of ENTSO-E, 10-year network development plan. So ENTSO-E is, for those who don't know, is the Association of Transmission System Operator. So all the European TSO are part of this association. The importance is in energy transition of new electricity interconnection is very high. Because by increasing power exchanges capability between countries, you can reduce the carbonized energy and produce more renewable energy. So being able to evaluate this increased power flow is very important for us. So to calculate this indicator, so that will be named ΔNTC in the presentation. This is the increase in net transfer capacity brought by a new project. A tool chain based on PyPowSyBl has been developed within an ENTSO-E working group and will be used for the next TYNDP. So this will be the topic of the workshop. So in the workshop, all the steps leading to ΔNTC calculation will be presented. So I will use Jupyter notebooks. So you don't need to have a Jupyter notebook Python installed or anywhere. I'm using Binder, so I don't know, for those who know, you don't have to install everything. Everything is normally installed somewhere in the cloud. The notebook will rely only on open data available. That means all the time series of load generation exchanges that you can find on ENTSO-E transparency platform, for example. The network models are public network models and are coming from the previous TYNDP, so they are a real model. And we will leverage PyPowSyBl to perform all the tasks involving network calculation or manipulation. So in the next slide, I will present you the global picture and all the steps that are involved in ΔNTC calculations. So the start is individual grid models. So they are coming from the TYNDP. And also the yearly country data, so load, generation, exchanges. So this is a yearly data, but hourly basis. So kind of 8,700 hours. With this data, with the individual grid model, we will use PyPowSyBl to import these models and to merge them. And just to show you how simple it is, just in a few lines of code, you import the model, you load it into your workspace, and you merge them. Once we have this model merged into PyPowSyBl, then you will be able to calculate sensitivity calculations. That means you will be able to know for every parameters, for example, load in Spain, generation nuclear unit in France, or cross-border exchanges, you will be able to calculate sensitivities. That means that what will be the impact of changing the load in Spain on the lines of the network. Gathering all these sensitivities, we will build a PTDF, what we call a PTDF matrix, which is basically, so here you can see all the lines of the network, so around 5,000 lines, and all the parameters we have selected. Multiplying the PTDF matrix times the what we call country data, we will have the yearly flows on all the on all the lines in N conditions. So N condition means we don't have any outage on the grid. The grid is complete. So it's interesting, but it's not enough. We need to calculate N-1 to be sure that every line, every flows on every line remains below its rating limits, even if any N-1, any outage occur on the grid. We will use the functionality provided by PyPowSyBl, which is LODF matrix. LODF means line outage distribution factor matrix, and it will be the impact of outage on the grid. That means if I lose this line on my network, how the flows will be spread on the remaining lines. So we have this kind of matrix. So here, for example, we have a Spanish line. If we lose this line, we will have about 60% of its flow that will go additionally to the initial flow of this line. So with this LOTDF matrix, we'll be able to calculate yearly flows in N-1 condition. So once we have the flows in N, the flows in N-1, what we want to calculate is how much can we increase the exchanges until we reach a limit. So to be able to know, to calculate the flows after a power shift, we will need also to calculate power shift sensitivities. Power shift sensitivities will be, if I increase the exchanges between two countries, what will be the impact on the line near the border. So here, for example, I have a power shift between France and Spain. I mean, I will increase the load in France and decrease the load in Spain. It will create a new exchanges, an additional exchanges between France and Spain. And here are the lines that are mainly influenced by these new exchanges. So for example, this line is around 40% influenced by power shift increase. once we have this power shift sensitivity, we can also extract ratings of lines that are already included into the model, and PyPowSyBl can just extract this data from the grid. So with all this input data, we will be able to calculate using a solver, so an open source solver, so from Google. We will be able to calculate the maximal power shift that the network can provide until we reach a thermal limit. So I've talked about ΔNTC calculation. So here we have just a single value. That means that we have to do this all this process for a base case, but we have also to calculate all these steps with the new project. If we have a new project, that means that here we will calculate a power shift, the maximum power shift that we can perform on the grid and in the base case. Here, if we have a new project, for example, a new HVDC project between two TSO, PyPowSyBl provides also the possibility to calculate sensitivity to HVDC. Then we will have a new maximal power shift that we can reach. And then by subtracting the two data, that will give us the ΔNTC and what will bring this project as new exchanges capabilities. So that's it. I don't know if you have any questions.
Yeah. How would you rate, let's say, the ease of use of PyPowSyBl and also the performances, because you're looking at huge sets of data, although it's not very time constrained on your side because it's for the kind of longer term?
Usually the time of load flow computation in PyPowSyBl is quite quick. But the thing is here, as we are using a sensitivity matrix, we don't compute so many load flows. Just at the beginning to perform to calculate sensitivity to parameters, but afterwards it's just a matrix computation, and so it's 1 or 10 seconds to have the full year. Yeah.
Sorry, maybe I'm from CGMES. Maybe you already discussed about my question in the beginning, but unfortunately I checked quite late. I was wondering why you use sensitivity matrix to quantify everything and not use AC load flows. I mean, mainly because this is to assess let's say long-term project. So why you use the DC sensitivities?
So you answered a little in your question. Since it's for planning studies, the AC convergence is always tricky to reach, and we don't have all the information that we need also to perform AC load flows, because you don't have reactive data or forecast reactive data at that time horizon. We are talking about 5 years or 10 years in the future. So we don't have this data. So you have to take big assumption, and the theoretical gain using AC load flows isn't real compared to the DC in this case.
Thank you.
Yeah.
Some question regarding the characteristics of the networks. They are static in this kind of modelization, or do you have some dynamic margin or something like this that is
What do you call?
The idea is that normally you fix as a TSO physical limitation of your line,
Okay.
and you take some margin in order to keep exceptional events constraints. And but sometimes you are very low on the margin. Maybe you could go further, higher in the margin. So could you use Powsybl to evaluate if you change this margin, if it is better for this power shift?
Yes, sure. This is typically you have, for example, new interconnection project. When the new interconnection project is just a reconductoring of the line, that means that you will increase the thermal limit of your line, and then the difference in terms of power shift will appear in the ΔNTC calculation. Any more questions? Okay, so thank you all for your time.